Hello, and welcome to the Flight Readiness Review for the Rowan RAS team on behalf of Rowan University. My name is Brianna Higgins. I am part of the development team, and I am the presenter today. Today we'll be covering the experience, roles, and responsibilities of each person on our team, a system overview and plan tasks for our UAS, the developmental testing strategies that we've performed, and our results of our mission testing. To start, let's meet the team. Our team is advised by Dr. John Smazel, and our team captain is Julia Constantinos. Our competition team and our development team is as shown. Julia Constantinos is a junior. She is the team lead. She has been responsible for the electronics of this project. She has a lot of experience in electrical and computer engineering and has competed in previous drone competitions. Brianna Higgins is a senior engineering student. She has acted as the electrical lead for the project, focusing on electronics, programming, and autonomous control. She has limited amounts of experience in UAS, but a great deal of experience in other electrical engineering work. Scott is a junior mechanical engineering student and the mechanical lead for this team. He has worked on the mechanical aluminum frame as well as some simulations. He has a lot of experience in drone racing and has also competed in a previous drone competition. Tim is a freshman who has been responsible for a lot of the electronics and power, and he has a great deal of experience in electrical engineering, embedded systems, and computer programming. Andrew is a freshman who has been responsible for our mechanical airdrop and our competition pilots. He has 6 years experience in flying drones and is a very experienced RAS drone pilot. John is a junior student who is responsible for a lot of our electronics and has a great deal of experience in electrical and computer programming, and less experience in UAS, but again has such great knowledge in electrical engineering that he could provide to the team. Jeff is a junior mechanical engineering student. He has worked with us on a lot of logistics and budget planning for the project. And Aaron is a senior electrical and computer engineering student who has worked on programming, object detection, and object classification and localization. He does not have much of any UAS experience, but has a great deal of knowledge in computer vision. Nate is a junior physics student who has worked on the mechanical team and has performed simulations for the project and has 2 years of RC hobby work. And Matt is a junior who has been responsible for assisting in the electronics and has basic engineering knowledge. Next, let's look at a system overview of our UAS and our planned tasks for this year. To start, our UAS is a custom-built quadcopter with a cut aluminum frame and a PX4 flight controller. In our electrical department, we have separate power systems for the flight controller and the high power motors. This is a low power system for the flight controller and a series of two 6S LiPo batteries for the high power motors. Regulation is provided through buck converters, and the onboard power monitoring of the Pixhawk is able to control both its low power monitoring and the high power monitoring of the motor system. In the mechanical department, we have cut aluminum framing, 4 18-inch carbon fiber propellers attached to 4 high-power motors, and 3D printed target supplies release mechanisms underneath the drone direct through a safe mounting system. For our software, we're running a autopilot supported by ArduPilot. Our intelligent flight planning is controlled through the Raspberry Pi, and we use a system of Python scripts on the Raspberry Pi to control the Raspberry Pi camera for object detection. As for the tasks we plan to accomplish this year, We are attempting the air delivery, autonomous flight, autonomous object detection and localization of markers, and stationary object avoidance. We will not be attempting object detection of persons engaged in any activity, and we will not be attempting moving object avoidance. As expected, autonomous flight has been very successful in our test, and we expect the success to only continue. Waypoint capture has been very successful, thanks in part to our work with autonomous flight. The obstacle avoidance is still in progress, and we're expecting that to also go quite well now that autonomous flight has been drilled down and successful. Object detection, classification, and localization has been very successful in its simulations, as we're using machine learning deployed on a Raspberry Pi, and as it stands, this is very easily extendable to autonomous usage. And our target drop system should be able to very accurately drop the payload from a vertical drop through the drone with great success. Now let's move on to developmental testing as we go into the methods and results of the tests performed in each subsystem within the drone. So our tests usually consist of those as follows. We have our unit tests of subsystems, which were performed prior to flying the drone to have an idea of how each system works in isolation. And as applicable, we had software simulations provided within each unit test to kind of guide our testing methodologies. Once each subsystem is passing its unit tests, it's added to the UAS for flight, and this ensures comprehensive and safe testing measures throughout the development process. As we look at our autonomous flights, we've had 4 fully autonomous flights and 6 partially autonomous flights, and all were a great success. No crashes were ever recorded. Very grateful for that. The pilot was trained to handle manual takeoff and landing, but the UAS was developed to be able to perform these tasks on its own. For each flight, prior to each flight, we would calibrate each of its peripherals, such as the accelerometer and the GPS, and this is done between each set of flights to ensure there's no damages incurred by any unknown sources between test dates. And our average time in the air for our autonomous flights is 7 minutes. Note there's a great amount of standard deviation on this. We simply chose several smaller tests for more rigorous testing, but we've shown that we are able to sustain a good amount of autonomous airtime. We are able to successfully capture waypoints in our autonomous missions. We have so far encountered every waypoint as desired. Our accuracy is variable depending on a tolerance we allow to the waypoint. As such, you can see in these middle runs, depending on the heading of the drone, it might skip past the waypoint on its path, and we can adjust this so that that curve does in fact cross over the waypoint simply based on a tolerance we can set. And the average number of waypoints in each of the missions we have tested so far has been about 6. As for obstacle avoidance, our initial test handled static object avoidance by loading waypoint files to the PICSOC4. Current development is looking towards replacing these static files with automatically generated paths from the Python library DroneKit, which is able to modify its true waypoints and target waypoints to maneuver around the obstacles. And this logic is just being handled with simple pathfinding algorithms, which are easily available in Python and supporting libraries. As for the imaging component, we've shown great performance here. Our image capture is on a Raspberry Pi camera mounted to the electronics board on board our UAS, which is always looking straight down for a bird's eye view of its environment. All images are a 640 by 480 pixel resolution, and as this is the common version 2 Raspberry Pi camera, all parameters of the camera are well known, which allows for efficient calculations in our computer vision algorithms, and the fixed mount system on our UAS has provided very reliable imaging over its flights. For detection and classification performance, we're using some machine learning APIs to create custom classification modules based on the targets we anticipate will be in this year's competition. We can see these systems were tested on the Raspberry Pi itself directly, which shows that once this is functional as just a single Raspberry Pi, it can be connected to the Pixhawk and deployed almost immediately. As you can see here is an example run of one of our more challenging tests, where we see in its first example it's misclassified a C as a U, which of course is wrong. With a good eye you can see why it may attempt to do that, so now we have some idea of how we can correct this, and we're retraining this algorithm now to better understand the nuances of the letters and their positions. Localization is performed as a result of our imaging software. It uses computer vision to calculate the pixel transformation needed to find the GPS location of each target, and our simulations have provided highly successful into this end. Our 3D printed air delivery system has been tested to ensure reliability. This involves a physical prototype, which is based on our SOLIDWORKS drawings of the components. The reliability of the dropper mechanism ensures adherence to proper tolerances, and SOLIDWORKS' verification software is used to further improve on these tolerances, so small corrections could be made to ensure the smooth transition of the release mechanism. And now finally, let's look at some of our mission testing procedures. These simulated mission tests are what we are attempting to do to best understand the missions we will soon face. Our current missions are run in a local tech park with the telemetry data received to the ground control station running autopilot. These tests conducted verify manual flight safety mechanisms, autonomous flight waypoint collection, and object detection and localization. Obstacle avoidance and airdrop are in progress, but our software simulations are highly promising, and we have basic prototypes to be developed within the next few days. As a result of these mission tests, we can show that the drone is fully capable of autonomous flight and can successfully follow a flight plan with autonomous takeoff and landing. As you can see here, our pilot, a jokester he is, let go of the controller for a bit to show, oh, I don't need to control this, it can control itself, which is a great testament to how well it flies. And through these tests that we can show, our unit tests of other modules, such as the object localization, show that this can be easily deployed on this system as it's very extensible and the autonomous control is highly reliable. Based on all this, we can give us a general score of how we believe we're performing at this time. As our previous mission tests have been quite short and our team always strives for efficiency, I would give us a 10 out of 10 on our timeline. As for autonomous flight, we've done excellent with autonomous flight in waypoint capture to date, and our only room for improvement right now is waypoint accuracy, which is definitely something to be considered more heavily. Obstacle avoidance, as we have chosen to ignore moving obstacles, so there's a bit of luck there. We're focusing on our stationary obstacles, which is still giving us points, but not as many points as we could have. Our object detection, classification, and localization algorithms are performing wonderfully, and we're simply waiting to make some tweaks to the algorithms and deploy it on the system. Our air delivery system, again, is still in development, but current simulations have been very promising. So as such, I would give that about an 8 out of 10. That's for operational excellence. It's a great team, so that's a obvious 10 out of 10. So as of now, we're looking at just a hair under 80% for our overall performance, which is great for our first year. I thank you for listening, and I look forward to seeing everyone down in Maryland this summer.